Hello students, this presentation will consider design of digital filters. The flow of the presentation will be, first we start with what is a digital filter, followed by the techniques that are available for the design of digital filters. I have divided this presentation into three parts. Okay, we'll first start what is a digital filter. A digital filter is represented by its transfer function h of z. You can see it accepts a discrete input signal x of n as input and gives out discrete output signal y of n as the output signal. If we want to use a digital filter, it is always used in this format. You can see an analog to digital converter followed by a digital filter, then we have a digital to analog converter. The entire dotted box represents an equivalent analog filter H equivalent of S. The inputs to this analog filter, you can see that they are analog in nature, both XFT as well as YFT. Right. An LTI system, that is linear time invariant system, can be represented by its system function or a transfer function h of z or by a difference equation. So consider a linear time invariant system represented by the difference equation. You can see the equation is summation from k equal to 0 to m bk x of n minus k. This is equal to summation from k equal to 0 to capital N ak y of n minus k. So take z transform on both the sides and setting all the initial conditions equal to 0, we get this. Take the ratio of y of z and x of z that represents the transfer function of h of z, transfer function h of z of the digital filter, which is nothing but summation k from 0 to m bk z raised to minus k divided by summation k from 0 to n ak z of minus k. Well, if the system is bounded input bounded output stable, its frequency response can be obtained by putting z is equal to e raised to j omega in the transfer function h of z. Also, one more important thing, whenever we want to use h of z, it should be always used in the format a to d h of z d to a structure. Let us now consider the various techniques that are available to design the digital filter h of z. The first method is bilinear transformation, second one is approximation of derivatives, and third one is impulse invariant transformation. The third method is not there for you in the syllabus. We start with bilinear transformation. I will consider the first mathematical representation of this transformation, how exactly we have arrived at that, and later on we move on to the properties of bilinear transformation. So bilinear transformation, consider a first order differential equation a1 y dash of t plus a naught y of t equal to b naught x of t. Let us call this as equation 1. So take Laplace transform on both the sides and set all the initial conditions equal to 0. I get this equation. Take the ratio of y of s to x of s, which represents the transfer function h of s. A stands for analog, right? Okay, in turn analog filter, that is nothing but b naught divided by a naught plus a1 s. This is equation 2. Let us go back to the integral calculus. Consider the fundamental theorem of integral calculus. We have y of t is equal to integral of t naught to t1 y dash of t dt plus y of t naught. Call this as equation 3. Now what I do is change these limits t naught and t1. Will do a bit of manipulation. Set t1 equal to nt. This should be t1 and t naught is equal to n minus 1 t. What is that we are trying to do? We are trying to replace this continuous time variable t into a discrete time variable small n, right? So once I put this in these limits, what exactly this equation 3 becomes. I get it as y of nt is equal to integral of n minus 1 t nt from n minus 1 capital T to nt y dash of t dt plus y of n minus 1 t. Call this as equation 4. Well, now whatever this entire thing on the right hand side of equation 4 is approximated using trapezoidal rule. So I get y of nt equal to t by 2 y dash of nt plus y dash of n minus 1t plus y of n minus 1t. Let us call this as equation 5. Now I'll use this equation 5, find out the values of y dash of nt, y dash of n minus 1t. In order to find out y dash for different values of whatever the time variable, what I do is I will use equation 1, and from here I find out an expression y dash of t. So I get y dash of t equal to this one minus a naught by a1 y of t plus b naught by a1 x of t. Right? What I do is now put t equal to nt, I get y dash of nt. Put t equal to n minus 1 capital T, I get y dash of n minus 1t. So find out those things, put it here, simplify. That's what I'm going to do in the next slide. So I get y dash of t equal to a minus a naught by a1. The same equation I have written here for your ready reference. So I do this. Put t equal to nt and I will get this equation. Put t equal to n minus 1t, I get this. Substitute equations 6 and 7 in equation 5. That is, this is the equation 5, y dash of nt and y dash of n minus 1t. So I will get this. Now I want to replace this y dash of nt by y of n. See, what is that I am trying to do? I started with y of t, y of nt, and now I am finally arriving at y of n. Similarly, x of nt by x of n. So I get this as y of n. Sorry, I have written y of n. It should be y of n equal to t by 2. The same thing, a naught by a1 y of n plus b naught by a1 x of n. Similarly, this one will be y of n minus 1 x of n minus 1 plus y of n minus 1. This is equation 8. Now take z transform of equation 8 on both the sides and set all the initial conditions equal to 0. What I get is y of z equal to t by 2. So you can see that this y of n, I will get y of z. For y of n minus 1, I will get z inverse y of z. Okay, so do this, do simplification, take out all the terms with y of z as common and all the terms x of z as common. Take ratio of y of z and x of z, which will give you h of z. So this will be equal to b naught divided by a naught plus a1 2 by t 1 minus z inverse divided by 1 plus z inverse. So call this as equation 9. Compare equation 2 with equation 9. So what is equation 2? Equation 2, you can see that h of s, which is nothing but analog filter, y of s by x of s, b naught divided by a naught plus a1 of s. In place of s, you can see that I have here once again b naught divided by a naught plus a1. So this is the place of s, 2 by t 1 minus z inverse 1 plus z inverse. So I get s is equal to 2 by t 1 minus z inverse divided by 1 plus z inverse. So this equation, whatever that I have put it in the box, is known as bilinear transformation. Let us interpret this equation, which will give rise to the properties of bilinear transformation. So that I will be doing it in the second part of my presentation.